time scaling. So we'll see the time scaling of a signal. Consider that a signal fn is there, where n is the time index, and this is a discrete time signal. This is a discrete time signal. So if in this signal, if we replace n with say 2n, just take an example. So what we'll be getting? We'll be getting f2n. Now, how this f2n is different from this fn? Basically, I'm just calling it, this f2n is the downsampled version of fn. So we'll see this. Let's take an example first. Consider initially that fn is this signal -2, 1, 2, -1 and 3. Suppose this is your signal and the time index is 0 over here. Then we want f2n. So it means basically you need to drop alternate sample. You need to drop this sample, need to drop this sample. We will retain this, we'll retain this, we'll retain this. So then f2n will be equal to -2, 2 and 3. So this is your f2n. Now try to understand this again with some other example. Okay, so this was the first example. Let's take a second example. Say fn is equal to, okay, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's take this signal. Okay, so we want to say we want to find f3n. In this case, again, what we'll be doing, we'll be dropping samples. Like we need to drop, in this case we need to drop two samples. So we'll drop these two samples. First we will retain this, drop these two samples, then retain this, then drop these two samples, then retain this. Similarly, from on the left side, we need to drop these two, retain this, then drop these two. So what is left with us? The signal f3n will be equal to 3, 6, 9, 12. So that's our signal which is left. Okay, so basically this f3n, is downsampled by a factor of 2 of this fn. Okay, so what we have seen is that, okay, when a discrete time signal is time scaled using a scaling factor greater than 1, okay, so in the resulting time scaled signal, the number of samples are generally lesser than the number of samples in the original signal. Okay, so this process is called down sampling, okay, of discrete time signal. Okay, similarly we can have a upsampling also. So upsampling. So for upsampling, basically the scaling factor will be less than 1. So let's take an example. Say you have a signal Fn and n is replaced with 1 by 2n. So you'll be getting f of n by 2. Again, let's understand this with an example. Uh, Initially say Fn is equal to minus 2, 1, 2, minus 1 and 3. Okay. So what would be f2n? So what would be f2n? Sorry, it's not f2n, it's uh, okay. What would be f of 1 by 2n? So what we need to do for that, we need to insert 0 samples between two consecutive samples. So we need to insert 0 here, 0 here, here as well as here. So what we got after inserting zeros is minus 2, 0, 1, 0, 2, 0, minus 1, 0, 3. So that's f n by 2. Suppose we want to calculate f of n by 3. So in this case, we need to insert two zeros. Okay, so our new signal will be minus 2, 0, 0, 1, 0, 0, 2, 0, 0, minus 1, 0, 0, 3. So this will be the signal. So in general, what we can say is f of n by k, say k is an integer. In that case, we need to insert k minus 1 number of zeros. Okay, we need to insert k minus 1 number of zeros. Okay, so what we have finally learned from here is that f of n, if in this signal n is replaced with say kn and k is greater than 1, so we'll be getting fkn, and this is obtained basically by dropping k minus 1 number of samples. Okay, we have seen this with an example actually, so no need to explain it again. And if we have a signal this, we are replacing n with n by k. Now let's again write it down. F of n, if we are replacing n with n by k, we are getting f of n by k. So this is obtained by inserting k minus 1 number of zeros between two consecutive samples of discrete time signal or sequence. Okay, so come to another topic, that is time reversal operation. Okay, time reversal operation. We also called it folding operation. Okay. Suppose you have a signal Fn, okay, and here if n is replaced with minus n, what will be getting f of minus n. So what we can say that this f of minus n is the folded version or time reversal of this fn. Okay, so let's understand this with an example. If fn is equal to say minus 2, 1, 2, minus 1 and 3. Okay, so this is the time index 0. In that case, then f of minus n will be nothing. So basically it will be nothing. You need to just interchange the samples. These two samples will get interchanged and these two samples will get interchanged. So what we'll be getting, basically 2 will remain as it is. Here we'll be getting minus 1 and 1. Here we'll be getting 3 and minus 2. Okay, so this is f of minus n. Again, this time index 0 will be at this location. Okay, let's take an example for this. Okay, let's just again take an example, or you can say a problem. Suppose we have a signal fn which is 0 for n is less than minus 3 and n is greater than 4. Okay, and it is 1 otherwise. So question is, what are the values of n for which f of minus n minus 2 is 0? Okay, so let's solve this. So basically, let me first elaborate this fn. Fn will be nothing. Fn is equal to 1, 1, 1. Say this is your fn. So what is f of n minus 2 first? Of f n minus 2 is nothing that can be easily obtained by shifting this arrow left by 2 time index. So it will be equal to 1, 1, 1, 1. However, this arrow will be here. Now, what is f of sorry, let me just write this in. So, what is f of minus n minus 2? It is nothing, it is just folded version. So, we'll be getting f of minus n minus 2 will be equal to 1, 1, 1, 1, and the arrow will come over here. Okay, so from here we can see, let me just write down the time indices. This time index is 0, 1, minus 1, minus 2, minus 3, minus 4, minus 5, and 6. It means this signal is this f of minus n minus 2 is non-zero. Okay, for the range, for what range of n? For n from minus 6 to 1, and it is 0 for what values of n? When n is greater than equal to 2 and n is less than equal to minus 7. So that this is the answer for this. For these values of n, this f of minus n minus 2 will be 0.